Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks, Ralph. So this afternoon, I'm talking about how to do research properly, as if I somehow know, but Tora wanted me to talk. And one of the things I will be saying is that it's good to have a plan. So I do have a plan, and that's what the Reconceiving machine learning is. I'm going to tell you about that briefly, but the majority of the talk is technical. I recently came across this great quote from an investor in Sequoia, and he says this: if you can't describe what you're doing in 10 words or fewer, I'm not buying, I'm not investing, I'm not interested, period. Right? So, and they mean it seriously. If you walk in asking for money and you cannot distill it in 10 words, you're out the door. They did this because these guys had such a pitch. And I thought that was pretty damn good. So what's mine? So I can do it with 7. So I don't know whether that's better or worse, but this is what I want to do. So reconceive, you know what that means? It's like take something that's already there, but think about it anew, right? So it's not necessarily virgin territory. It's figuring out a new way of looking at stuff. But the how is the crucial thing. Systematically, you know what that means? Relating problems is the key thing here, right? So I'm looking at different problems and how they relate to each other. It's really just a stance. It's a viewpoint that I've been taking. Logically, you could ignore all of this gumph in the next few slides and just look at the technical stuff. From my perspective, I wouldn't have looked at these particular technical problems if I didn't have this perspective. Therefore, I think the perspective is valuable. You can make up your own mind. One thing I realize is that, normally when you try and do research, you're thinking you're going into bold new territory. You're an explorer in the Wild West. You're carving out a new area where no one has been before. But what I'm doing is more like brownfield development, as they now call it. You take an old site that was previously used for something else, and you build over the top of it in a different way. This used to be a Roman farm a while ago, right? And now it's a research lab. I'm working on a shorter time scale than that, I hope. I make the point that I actually think this is harder. I mean, I've done the let's do a new thing. I actually find this stuff more challenging. So that's good, because as again you'll hear this afternoon, I think one of the good things to do to keep yourself feeling young is to do stuff that's new and different. So I reckon that this is harder, but I claim it's got a bigger payoff. That's my big bet for the next 10 years. We'll see. Now, when you start thinking about, taking this big picture view, there's actually a couple of ways you can look at that. And I found this very useful analogy. So this very ancient quote was not discovered by me, but by a whole series of authors. I read about it in a book called Expert Political Judgement, by a guy called Philip Tetlock. And so what he was interested in was the following question, which will be interesting to machine learners. You have all of these political pundits saying, based on all of this stuff, we reckon Labor's going to win. Or we reckon that the Soviet Union will collapse, writing in the late 80s. They make all of these pronouncements, right? People who digest newspapers or Project Emporia, they suck all of this stuff up. And you think, this expert commentator, he says that it's true. How often do people go back and check whether they were right or not? So this guy, Tetlock, did. He gathered the data, waited 20 years, right, 20 years, then he went and had a look to see how well they did. And he did it in a very numerical manner. He used scoring rules, which I'm going to talk about, and found interesting things. One of the interesting things he found was that the foxes, which are the people that don't have some big overarching grand theory, are much better at predicting. Much better. So I figured that's a useful lesson. Here's some examples of what I would think of as a monistic approach, right? There's one big story. So the classical Bayesian methodology, you take Richard Cox's axioms, you say this is the right way to represent uncertainty, everything follows from the calculus of probability, full stop. Everything else is mere engineering and calculation. I'm exaggerating, but That's okay, I'm the speaker. Complexity theory, right? Actually, information is the most fundamental thing in the world. You know, there are physicists that derive the laws of physics from information. One of the best titles of a paper I've ever heard is by John Wheeler, where he succinctly described this as it from bit. Right? The world comes from information, it from bit. Or decision theory, which is sort of my background and where I started from. You know, you compose everything in that fashion. So my lesson from, you know, reading more widely is that perhaps don't get too enamored of just one way of looking at the world. So there's reasons for that. It's very hard to get it right first time. If you want to try and understand a whole field and you pick your framework, then you will go and justify everything into that framework. Right? It's like this great quote by John Kenneth Galbraith, you know, when people are presented with evidence that may require them to change their mind or prove that they had the correct opinion, most people get busy working on the proof. It's very easy to get yourself into a mindset and then justify it rather than, you know, look more broadly. Monism's great if you never encounter other points of view. But if you do, like in you know, monotheism, you either have to disagree with them, kill the proponent, or both. And I don't want to do that. And typically the world doesn't cooperate. You have a grand theory, the world's a big mess. So, whereas if you take this pluralistic approach, you can have lots of different little theories. It doesn't have to be part of an enormous, single, beautiful, overarching plan. It's useful in lots of other areas. I've already mentioned that Tetlock shows that foxes, who are the pluralists, do a lot better. So I'm betting that it works in machine learning. It's all about respect and mutual understanding, right?
By the way, can you explain, what about the fight? I just don't get the zoological.
The fox and the hedgehog. So this quote, look, I don't actually get it either, to tell the truth, but I'm telling you, this is this ancient Greek poet, right? He reckons that the fox knows many little things, but the hedgehog knows one big thing, right? Foxes are canny. They'll find lots of ways of escaping, right, from a predator. The hedgehog knows one thing.
Oh, that.
Yeah, that's it, right? It's a good one, right? But that's all that he knows. So it's been used as a metaphor. There was a famous essay by Isaiah Berlin who used it, so it's just a convenient thing, right? It's a... you know, I could have used the abstract words monist and pluralist, but they're a little dry. Okay, so it's about relationships. That's what I'm talking about. So what do I mean by relationship in this context? So you can talk about a particular object and think of ways of representing it, right? You can think of that as a relationship, and I'm going to give you an example of that. You can talk about binary relations between objects. Define two objects of interest and look at, there's all sorts of relations you can define between them. You could also have relations between their representations. You can talk about primitives, by which you can express a compound object in terms of primitive objects. And I've done some work on that, which I've previously spoken about, but I'm not covering here. Or you can talk about domination relationships. You know, one thing is always better than another. So, for example, in economics, people are interested in this. If you think of some of the sophisticated economic modelling done in computational advertising, it builds on this stuff, which is related to the basic stuff on experiments I'm going to talk about. So that's the general intro. And the three technical things that I want to talk about are the convexity of composite proper losses, and I'll motivate and explain that. So that's a relationship in terms of representations. I'm going to look at two different classes of estimators that are quite classical. They go back many decades, and one of the things I discovered whilst I was here is a seeming new relationship between them where you can express one in terms of the other. And the last thing, which I'm not going into great technical detail, it's much more of a current work, is the connection between different ways of representing uncertainty that the economists have developed over the last half a century and how that relates to the kind of prediction problems that we're interested in machine learning. Okay?
Is the goal to create a taxonomy of machine learning?
So that could be one outcome, right? I mean, my overall aim is to be able to understand all of machine learning. I think that's impossible to do at the moment, right? I've got the NIPS proceedings up until when they finished publishing paper copies on my shelf back home, and it's that wide. You can't get that in your head, right? if you count, as my postdoc did for me with a clever web script, the number of machine learning papers published in the tier 1 literature since 1960, there's over 20,000. So if you print it out, it will reach the roof. So that's a lot of stuff, all right? Now, how could you get your head around that? So that's my motivation. So what's a proper loss? A proper loss is a loss for a binary prediction problem. It imposes a structural dependency between the partial losses, which I'll explain on the next slide. The constraint that this imposes, the properness, means that the loss can be represented as a one-dimensional function instead of a two-dimensional one. Now, convexity of a loss is important in practice because you typically want to minimize the empirical risk, which is a sum of losses, and a sum of convex functions is convex and thus easy to optimize. So you'll see shortly why this is not a trivial problem, because can't you just say, well, all of the convex losses are the ones that you're interested in. So this is what I do. I characterize the convexity of proper losses in terms of their associated weight function. In fact, I do a little more than that. So here's a notation. You have labels, which we'll just think of as plus or minus 1, and predictions v. They might be real valued. Now, if you think of predicting a binary outcome using a linear classifier, and you want to predict the probability of a positive label, then you've got to map a real number into the interval 0, 1. So like with support vector machines, people use a thing called Platt scaling. John Platt invented, right? It's called a sigmoid. And you map that real number to something in the interval 0, 1. Now the statisticians call that a link function. So, sorry, I'm getting ahead of myself. I need to define the partial losses, which is just where if the label was minus 1 and you predict v, this is now just a function of one argument. This is the other partial loss. So I'm going to be considering this situation, right, where it's like predicting will it rain or not. I want to give a real number between 0 or 1, and what do I actually observe? It rains or not. A composite loss is one that can be written like this, where this little l takes an argument here that's in the interval 0, 1. This v might be the output of a linear classifier, so it's a real number. So now I've got two knobs, the choice of L and the choice of the link function psi. And it's just a convention. I don't really know why, but they always write this thing as the inverse function. Right? It's just a convention. It's an invertible function. So to talk about this in a theoretical way, you introduce the notion of a conditional risk. So normally you think of having x's and y's. Given it in x, you try and predict, given that feature vector, whether it's going to rain or not. I always just take the conditional perspective here. I can ignore the x's for most of the work that I'm doing. And so if we now take the expectation of y drawn from a Bernoulli distribution with probability eta, this thing becomes that. Now I've got this function here. This is my estimate, right? Eta means it's a probability. Eta hat means it's an estimate. That's a real number between 0 and 1. And this is the true probability, which we don't know, right? We don't know what the true probability of rain is. Well, we do in Cambridge, but we don't normally. So that's the conditional risk. And then the best that you can do, right, the best prediction that you can do is you just minimize this, okay? So you want to take the smallest value, you optimize over eta hat for this thing, okay? Now, a proper loss is a loss that has this property here. That is that by choosing eta hat equal eta, you will minimize it. Now, there's an infinity of losses that you can construct that don't have that property. It is a constraint on the loss function. If you just think of the loss function as a mathematical object with two arguments, not every function of two arguments is going to have that property. Yep.
Why is it the conditional risk called conditional?
Because I'm conditioning on the x's, right? So you see there's no real x's here. They're kind of hidden, and you can do all of this work without that. At the very end, the real prediction problem you want to solve for your boss, you'll be taking another expectation, and these etas will actually be functions of x, and you'll be taking an expectation over the x's, but I'm hiding all of that.
Is there some assumptions about the sampling of the training and test distribution or anything like that? I mean, are you
Yeah, implicitly, it's all the standard statistical decision theory thing, right? So that, the way you would want to use this is that the world gives you stuff that's drawn from a probability distribution, you get IID samples, and you want to optimize, okay? Right, so this is the condition on a proper loss. It's not any old loss, it's a loss such that if eta hat equals eta, then you've minimized it. Now that's the kind of loss that you would like to use. It's a fair loss to use. If the probability of rain was always 70%, and you as a weather forecaster always predicted it's a 70% chance of rain, then it's good to have a loss function that tells everybody else that that's the best that you can do. So that's the point. And a proper composite loss is just a proper loss composed with a link function. And here's what a proper loss looks like. This axis here is eta. Axis going in there is eta hat. So I've got this function L of eta comma eta hat. This green line here going across the diagonal is L of eta comma eta, of course, which, because it's proper, is actually the Bayes risk. And it's a theorem that says that that line is always concave for a proper loss. So, the exact shape of this can vary a lot, but that convexity is always there. And because of that convexity, it turns out that you can characterize a proper loss, which is a function of two variables, in terms of a function of just one variable. It's a structural constraint. So this is not new. It goes back at least to the 1960s, although doesn't seem widely known in the machine learning literature. At least I've never seen it in a machine learning textbook. And what this says, and here I've written it for the composite loss, which is the link function just keeps track of a change of variable, basically. What this says is that a proper loss can always be characterized in terms of these two functions here. So this is just the first derivative of the link. The link is monotone, so therefore this thing's always positive. It's like an unnormalized density. This thing also is a positive function. In fact, it's equal to the negative of the second derivative of the conditional Bayes risk, which I showed you in the previous picture is always concave, therefore the negative's convex, therefore this thing's always positive. So given any composite proper loss, you've got these two functions of just one variable, and conversely, if I pick any one of them, I can construct a proper composite loss satisfying this equation. Okay? And in the case where you've got no link function, it's even simpler. And you see here, this is the constraint. I've God, no matter how many times you check your slides, that should be a subscript -1 and a subscript +1. So there's a constraint between the two partial losses. Here's some examples of losses. The simplest one is the square loss. So here are the two partial losses. The weight function is just constant. Here's the 0-1 loss, right? You just get the sign of, you just predict whether you're on the correct side of a half. Its weight function is a delta function at a half. This is log loss. Some people call this boosting loss. I don't actually understand why it's called boosting loss. It's just a name, right? Given any of these, it's just a calculation, mere calculation to work out the weight function. The weight function's got a nice interpretation as well, which we might get back to. So the first result is now, hopefully you realize why it's not entirely trivial, is a characterization of the convexity of these composite proper losses in terms of those nice one-dimensional functions. So rather than thinking of a two-dimensional function, which has got a lot of freedom, we've reduced it to two one-dimensional functions. And what this says is that if this equation holds, then the composite proper loss is convex, and conversely. So it's a necessary and sufficient condition. Now, parsing that is a little tricky, but if I just show you a picture, you'll see what my notation tries to capture. If I plot the weight function, and if I normalize the weight function so that at a half it equals 1, and I know that doesn't work for 0-1 loss, but I'm sweeping that under the carpet, and observe that if I have a loss function and I multiply it by 2, it doesn't change anything from a machine learning perspective, right? Right? So I can go and do that normalization. Then what the theorem says is that if the weight function lives in this yellow region, it's convex, and if it doesn't, it's not. Square loss is just this constant going through here. Okay. That's the story when you've got no link function, but the theorem is such that it can easily take account of a link function. So if you use the logistic link, you just end up distorting that picture. So this shows you some interesting things. The 0,1 loss is just a delta function here. Now, okay, maybe take a limit. You'll remember the way you think of a delta function, or the way engineers do, is it's just a limiting process. So if you had a big spiky thing there, then you go and say, well, what loss function is closest to that? You might want to take this one, right? What does he correspond to? And that actually corresponds to a loss where the partial losses are linear over part of their range. It's kind of like if you think of all convex functions, you go to the boundary of the set of convex functions, you're going to get linear functions. So this parameterization is interesting because it suggests a way you can implement something called surrogate tuning. So this is not the idea of surrogate tuning is not mine, but the rest of the stuff on here is. It turns out if you want to minimize the 0,1 loss, which is often the case for a real prediction problem, you can't implement that because it's a non-convex function. And so what people do, they'll use something like a hinge loss. That's a convex surrogate. Okay. Now, if you want to make sure that you predict class probabilities correctly, as well as the labels, then you'd want a proper loss. So then the question becomes, what is the best convex proper surrogate loss to use? It turns out that no such thing exists because the best loss, so it's a little tricky to define, and I haven't put this in symbols, but just trust me, there is a natural way to define what best is. However, it depends on the underlying distribution. So I can actually construct a situation, two different distributions of the data, two different composite convex surrogate losses, and on problem 1, loss 1 beats loss 2, but on problem 2, loss 2 beats loss 1. That says that to do the best possible, you've got to depend on the actual data. So then what you'd like to do is to explore over the range of possible losses. To do that, it would be nice to have a nice parameterization. How do you explore the space of two-dimensional functions with a constraint? So that's the idea, right? So the key result there is that there is a nice slick characterization. It's got some intuition. It suggests a way of developing strategies for doing this surrogate tuning. I have not done the surrogate tuning. I've made a theoretical suggestion. Hopefully someone else will pursue it. So there's the take-home message for this part. By looking at the whole set of all possible losses, you get some insight into the way that they behave.
So you said on the previous slide it needs some low-dimensional characterization.
Yep.
Of W. W is a unary function. So what do you mean by that?
It's a function of one variable is simpler than a function of two variables, but it's still an infinite dimensional object. So I could, like I'm thinking polynomials of degree 5.
Okay.
Now that would be a crazy thing to use, but there'd be some nice way of doing that. In fact, I have worked out a few candidates there. You simply want to exploit the fact that it's always positive, right? Think of all of the finite dimensional representations of densities there are around and use them. Because the only difference between W and a density is that W is not necessarily integrable. Okay, so that's the take-home message of this part. And as a side effect, for those of you who know what a Bregman divergence is, this characterizes when they're convex in their second argument. For those who don't, I'm not going to explain it. Okay, so the second topic I'm talking about are M and L estimators, and it's not my terminology. I would not have chosen that terminology, but it's in all of the textbooks. If you look at books on robust statistics, they are often looking at very simple statistical problems where you're estimating a single parameter, like a location parameter. So the usual argument about robust statistics is that, well, if there's a few outliers, then what was a good efficient estimator becomes a lousy one. So they try and look at all different ways of designing these estimators. And there's several different quite distinct classes for doing so. So what I will show now is how these two different types of estimators are related to each other. And I'm making a simplifying assumption here, which is not essential, that I'm basically estimating a one-dimensional quantity and everything lives on a finite interval. So first I'll define what an M-estimator is, then an L estimator, and then what the connection is. So an M-estimator, and the M is supposed to remind you of maximum likelihood, and straight away just keep track of, we write it as an arg-min, right? You can always flip min and max. An M-estimator is generally of this form. So f is some function, the xi is your data sequence, and you've got to optimize over t, and that gives you a statistic. You can see that that is effectively the empirical version of this continuous analog, where you just use the empirical measure. Right? So that's an M-estimator. An L-estimator is a linear, alpha linear, combination of order statistics. So the order statistics, you just get the sample, sort it, and index into the sorted set. And here you've just got a linear combination. In fact, the general form, it's a linear combination of a nonlinear function, but I'm going to ignore the h for now. You can write that as the empirical version of this, where now we are using the quantile function of the random variable of interest. So f is the cumulative distribution function, the quantile function is just the functional inverse of that.
So if I took the median, for example, it would just be the n over 2?
Yes, yep, so I've got the median.
With 1 and
Yep, so I've got the median on the next slide.
Oh, and M was A, right? In the previous.
Sorry?
M is A.
M, yes,
Capital M,
yes.
capital A.
M corresponds to these weights. Yeah. So a simple example is indeed the median. So the median is you just take this quantile. But here's the observation, right? So in this special case, there's already a connection. And when you first look at this, you think this is a bit magical. I can either just write it as that. That's a linear combination of order statistics, just one of them. But here, that's equal to that if I happen to choose this magic function here. Right? And you think, well, why is it of that form? But you can check that this does indeed work. So if I optimize this with f equal to that, that is the median. Okay? You can get any quantile you want just by adding another little offset term here. So I came at this because I was actually interested in understanding graphical models under different loss functions, and discussing with Tora, we thought representing things in terms of quantiles would help. And I thought, how do you think about quantiles more abstractly? And in this difficult to read paper, I found a way of doing that. So Kolchinsky actually looks at this object, which you can see looks like that one, but now I've got this additional parameter here. If v equals 0, I've just got that. So it's like taking something that's just a single number and now taking a whole function of it. And as often happens in mathematics, you go to something a lot more general and it becomes a lot clearer. In this case, okay, I've got it on the slide. So this is the magic F that you should use to get any quantile. So my observation was, look, if it works for quantiles, why can't it work for everything? And indeed it can. And the thing to take away here is not the technicalities. I mean, I haven't figured a way of making this look less gory yet. But let me try and explain the gist of this. So the result basically says, under mild technical conditions, any M-estimator can be written in terms of an L estimator, right? They're equivalent. And I can explicitly work out the connection between them. I have to define a number of objects. So I start with this f function here. That defines my M-estimator. I write this thing here. I take its second derivative. This thing's just a functional of the underlying distribution. Then I take effectively its cumulative distribution, although I'm not claiming that it's normalized yet. And I also have this quantity here. Then what you can prove is that this is your M-estimator, or rather this generalization that Kolchinsky developed if v equals 0. And over here, look what you've got. This thing is like a distribution function. it's not normalized, but I've got the inverse function here. So that's like a quantile. And okay, I've got to evaluate it at a certain argument, and this B thing is going to be something that depends on the distribution. But you'll see when I show you a special case shortly why this seems interesting. The proof, which I'm not going to even talk about at all, is just based on Taylor's theorem. If you check the general theorem, you can recover the standard results. So you can check that it works for least squares regression. So in the very top of the slide, you can see the function that you use for least squares. You optimize that, and indeed, as is well known, if you optimize least squares error criterion, you get the expected value. That's what we mean when we say we're doing regression, right? You've got this data, you want a regression line. It's the conditional expectation. Why? Because you've minimized the squared loss. It also works for the median. So these are just sanity checks, right? So just trust me that I've done the sanity check. I can refine the result. I had this object that looked like a cumulative distribution, but it wasn't normalized. If I just go and normalize it, it just makes life look a little nicer. You get a similar flavored result. This A was B on the previous slide. It's just a constant. You can think of it as just an expected value, right? X is the random variable. Now this is the key thing to look at, right? And I'm going to show you some interesting thing that happens in a certain special case. Well, I've already said this, that it's a quantile. And this thing here, right, this is one of the intermediate quantities that I defined, where this thing was actually of that form. But if I write it in this general form here, right, you say, oh no, this looks interesting, right? You might say, that's just an integral operator. Or you might say, this looks like a kernel density estimator. And that's the intriguing thing that I wanted to show you. So if you think of this as an integral operator, what that actually means is that this object is the density of the random variable obtained from the original distribution via some nonlinear transformation. Now, I don't have that explicitly in general, but the interesting case is when you look at the situation where this function, so our whole family of estimators parameterized by f, if I take f to be this translation invariant form, then I just substitute in, what I get is that the magic quantity ends up looking like this, right? So this capital D inverse, that's the quantile of a cumulative distribution function. That cumulative distribution function corresponds to this density. This density corresponds to this, right? This here. Now, this is a kernel density estimator, right? So this is the intriguing thing. You start with an M-estimator, which is an optimization with this function f(st). You take this particular form here. You take the second derivative of that. One of the assumptions is that f is convex. So if f is convex, phi is convex, its second derivative is always positive. So phi double dashed is a positive function. This is a sensible kernel density estimator. So it's like I take my data, I feed it through a kernel density estimator. That gives me a nice smooth density estimate. I construct a cumulative distribution from that smooth density. I take the quantile of that, and that's the M-estimator. I found that pretty weird, right? And it seems to be new. I've spoken to statisticians, and I think it's, well, you'll see on the next slide. I say why, what the value of that is. The intuition came from my observation that this kernel, that is the right one to use for the median, that is actually the kernel in the Taylor's representation, which I've used before. So you can write Taylor's theorem with the integral remainder term, and you can express it in terms of a kernel like that. So that was the observation. Then I just go and take the original definition of the M-estimator, represent the convex function using Taylor's theorem, interchange the order of integration, argue that that's legitimate, and we're done. I have no idea what the use of this is, right? But it does seem intriguing that you've got these two completely separate classes of estimators. They're typically discussed in separate chapters in textbooks, but now you can see, actually there's some connection there. So, yep.
There's this robust estimator where you take off some points from the top and some from
The Windsorized, yep.
and then you take a squared loss
Mm-hmm.
kind of on the remainder. Does that fit into this framework? It's kind of a mixed case.
Understand. I'm not sure. No, it's a good question. I just don't know. I'd have to think about that a bit carefully. Yep.
So mentioned that there are certain assumptions under which this mapping exists.
Yep.
What are those assumptions?
The f function is convex, which is what you normally assume anyway. And the only technical thing I do is to interchange the order of integration, and it suffices for that if everything's living on a compact interval. So it's really very mild. Okay, so the last thing I want to talk about is the connections. Yep.
Just technically, do you really need to track the absolute value of x?
That
keeps it positive, or that keeps it at 0 or something.
this is a trick, right?
There's a trick in there.
It's at one level you don't. It's a way of avoiding a cancellation of two infinities. So it's a trick.
Integral.
Yeah, in the integral.
Because in the discrete case, you don't need it.
Yeah. But when you integrate, it keeps all of the integrals well defined.
Okay.
Yeah. There's all sorts of affine invariance with these things. It's like with if you're representing if you've got a convex function, and if the thing that matters is the second derivative of that convex function, then I'll get the same second derivative of the original convex function or the convex function plus an affine term. So you can think of this as just the affine term. It doesn't actually change the result, but it keeps all of the intermediate steps well defined. Yeah. Yep.
Does it generalize to a multivariate case? Or?
Yeah, so the abstract development is, I don't see any reason why it would not. Yeah, because the only trick is Taylor's theorem, and I've used exactly the same form, the multivariate generalization of that. The thing is, So what you'll get there is, because I'm using this framework of Kolchinsky, there is a natural meaning that comes out of this theory to what a quantile is in the multivariate case, and you will get that, right? Now, the connection with the kernel density estimate for the translation invariant case, I have not thought that through. I don't know. I mean, this seems weird enough already. Okay, so the last thing I want to talk about briefly is connection with economics and finance. So suppose you're using your machine learning to predict all sorts of financial quantities. There's all sorts of questions you want to ask there about how you evaluate performance. What loss function should you use? It's a very natural situation where you want an asymmetric loss. I mean, often in machine learning, people will take these loss functions off the shelf. If you're predicting in finance, a negative result is much worse than a positive result of the same magnitude. Right? You might go broke, but it doesn't hurt if you do particularly well. And this is related to something that many economists have studied, which is how you evaluate the risk of a portfolio. Now, this is big time stuff. So, for example, all of the banks, the central banks of the Western world countries, they have all of these rules about how much cash all of the commercial banks have to have on hand. Now, the way they work that out is by doing this fancy risk analysis. And the way they do that risk analysis implicitly involves the choice of a loss function. So this question of choosing the loss function correctly, if you get that wrong, can lead to the collapse of the entire banking sector. So this is not my opinion, that's what a lot of economists think, and they think that this is a very serious matter indeed. And so they have all of these big international agreements about what loss function to use. And they get it locked in terms of these multilateral negotiations. It's amazing, right, that this stuff even exists. So if you look back to how the economists deal with uncertainty, my view is I learned a lot from doing this, and they seem a lot more sophisticated than we are about it. So back in the 20s, a guy called Frank Knight distinguished between what he called risk and uncertainty. Risk is where there's probability distributions and it's meaningful to talk about expected values. Uncertainty is where it doesn't make sense to talk about that. Now, there are situations where you've got repeated examples or something where probabilities make sense. It turns out through the history of economics in the last century that the notion that you keep these two notions separate is very important. At the same time, John Maynard Keynes had the same distinction that he made in his book In the Theory of Probability. And he used that as a basis for arguing why, in general, you should work with interval-valued probabilities. There's some very famous work that's led to a Nobel Prize in the 1950s by Maurice Allais, and another piece of work by a guy called Daniel Ellsberg, who's interestingly, you look this guy up, right? I thought, it's good to learn the history of this. I looked him up on the Wikipedia, and I thought, God, this can't be the same guy, because there's this huge long article about Daniel Ellsberg, who was the guy who released the Vietnam papers that basically brought down President Nixon. It was the same guy, right? So he did a PhD on this stuff, and then he went to work for the military, thought that the US government was doing all sorts of bad stuff, leaked 7,000 pages, and he was on the news a week or two ago when WikiLeaks published this gargantuan dump of information on the Iraq War. So that's what he ended up doing after the theoretical stuff that I've studied. What he did was he studied a thing called uncertainty aversion. So many people will tell you that the way people behave under uncertainty is that they minimize expected loss, right? They're rational agents. You talk to Susan Athey, your chief economist, she'll tell you this is what people do, okay? There's evidence going back to the 1950s that show people don't, right? It is well understood that they don't. And the Ellsberg paradox, for example, constructs a situation, two situations, both with exactly the same expected utility, but one of them's got more uncertainty. And people behave, it's called uncertainty aversion. They'll always pick the one with the less uncertainty, even though the expected risk, and even if you prove to them the expected risk is the same. So why is this interesting? Well, okay, machines could behave rationally, right? You think, why would you need to worry about that? But observe, what happens when you do machine learning? Ultimately, it gets interpreted by a person. So I think you do have to think about this, right? It's sort of like, in engineering, you talk about the interface between one module and another. So I'm thinking about the interface between the machine learning with uncertainty interfacing to people. What kind of signal should be on that wire? All of this stuff tells me that maybe there's something richer than probability. So that's kind of the motivation. And the particular stuff that I've been looking at, which I'm not going into any detail, talks about these coherent risk measures. So it turns out you can define a thing called a risk measure. It's basically a functional of a random variable. You can define it axiomatically. You want it to have a property called coherence, which is related to convexity. And this is the thing that's in the Basel II Accord, right? So what you would like is that if I've got all of these different stocks, represent them as probability as random variables, if I take a diversified portfolio of stocks, I would like the risk of that to be never greater than the risk of individual ones, right? So you want this idea that diversification enhances your risk. Not every risk measure has that property. The one that the banks use at the moment is called value at risk, which is just their terminology for quantile. So that's one of the other interesting things that I've learned here. Getting into another field, they use the same ideas, but they call them different things. What we call a quantile, they call value at risk. One of the ideas that they do use is a thing called the conditional value at risk, which is the conditional expectation conditioned on the random variable being greater than a certain quantile. Now here's the interesting thing. These risk measures, you can study them in the same way that I've studied loss functions. You can represent a risk measure in terms of a weighted combination of primitives. It's the same thing as the weighted combination implicit in the composite losses that I was talking about. Remember I had a weight function? I didn't put it up on a slide, but it turns out that every proper loss can be written as the weighted combination of a whole bunch of elementary losses, and the weight function tells you how to glue it together. The same thing happens with these risk measures, which is why I got into looking at this. So that's kind of a super fast summary of that. So here's what some of the takeaways I get from studying this. Probability is certainly not the universal answer. Now here I'm going to demonstrate that in something that I've learned, and this is not new. It's new to me, and maybe it's new to you. Suppose you start with a traditional Bayesian setup, right? You're going to assume that the world generates stuff probabilistically. You go and construct your prior. You now know what to do. It's just mere computation. But then you have some doubts. Maybe I don't have the prior exactly right. So I want to robustify it a little bit. Okay? So rather than thinking of a point prior, I have a set of priors. Right? This is, you read Berger's book, he talks, this is called robust Bayesian inference. So you do that, and now what you do, you behave pessimistically at this meta level. You take the worst case over the set of priors. Right? You could argue that, yep, I'm still being completely Bayesian, it's all completely rational, it's a completely fine thing to do, which I think it is. But here's the interesting thing. These guys in 1989 showed that if you do that, then that is equivalent to doing your whole inference process using an uncertainty calculus that's not probability. So they've got a representation result. So instead of using probability, so probability is an additive set function, right? It takes its arguments as sets and it's additive. These things, these Chauquet capacities, are sub-additive set functions. And so there's this amazing representation result that if you do this worst case over a convex set of priors, has to be convex, then that's in an if and only if relationship to a Chauquet capacity. Right? So it's just one, you choose one or the other, you'll always get the same answer. So this made a big deal in the economics literature. I think I can skip that. And, just because I'm leaving, indulge me for 30 seconds. An interesting reminiscence. The stuff I did for my PhD was analogous to this robust Bayesian inference thing. Have two random variables, I want to calculate the distribution of their sum. If I know the marginal distributions and I know they're independent, it's trivial. I just convolve them. What if I don't know that they are independent or not? All I have is the marginal distribution. Again, you do a worst case. It's analogous to this Gilboa and Schmeidler stuff. And what happens? What falls out of that is the calculus of fuzzy arithmetic. So this, rightly so, oft-derided theory of fuzzy numbers turns out to be derivable, as a theorem, from probability. So it's like probability can induce all of these very interesting, highly nonlinear calculi, just depending on the way you set up the formal problem. And teaching myself about this stochastic finance stuff, I go and read in books that these finance people use this. So that was pretty funny. I thought it was funny. My conclusions. I've sketched my overall research agenda and explained why I think it's useful to look at these individual problems. I've shown a couple of concrete technical results which are new, I think show interesting relationships, and which certainly for me I would not have looked at if I had not tried to take this viewpoint of gluing stuff together. That's advertising. And I'm done.